going to look at likelihood in linear regression. So again, we have this kind of model, y is x beta plus some error, and we've said before that we assume the errors are independent, zero mean, constant variance. So the zero, they have constant variance, and they're independent. If we add one further assumption that they are normally distributed, so P of I is normally distributed, mean zero, constant variance sigma squared, we can then use this to perform maximum likelihood inference on this model. Now, before we look at how what the maximum likelihood estimator will be for beta, let's just look at some of the notation that we could develop for this model. So what I want to do is break the model into pieces. So we said we have response variable, we have some parts that we've been considering as a constant, and we have an unseen random variable. So this is a random variable, and it's a random variable because it's a function of a random variable, and this random variable we've said is a normal random variable. Now, if we do a little bit of rewriting, we actually take this part of the model and we're going to denote this by the symbol eta. So eta is equal to x beta, or if you prefer the notation, beta 1 plus beta 2 xi2 plus all the others until we have beta p xip. Doesn't matter, we can call this the linear predictor. We can call it the deterministic part of the model, but we've just introduced this other piece of notation now, this symbol eta. We can also talk about y being a normal random variable, but it's a conditional normal variable, and it has a mean given by x beta and a variance given by sigma squared. So we can either state the original model where epsilon is zero mean, variance sigma squared, or we can write that y is a normal random variable, and do note it's y's conditional normal. Each y sub I will have a separate mean given by this linear predictor. Now, a very small point of detail that we don't need to worry about at the moment, but we will think about this later. What we're saying is that y is normally distributed with a mean given by the expectation of y and the variance given by sigma squared. And in this particular case, we've said that the expectation of y exactly equals eta of I, which we've said is the linear predictor xi beta. Now, there's some overloading of symbols here, but there's an overloading for a purpose, because we now have two parts to our model. We have this linear predictor, the deterministic part, and we also have a random component, sometimes referred to as a stochastic component. And somehow the deterministic part has to be linked through the expected value to the random part. and in this case we've linked it using an identity function, so that the expected value is exactly equal to the deterministic part. But clearly, if we alter the function that we use to make this link, we can have much more flexibility in choosing the random component and in the way we link the random component to the deterministic part. We don't need any of that detail for now. For ordinary linear models, they collapse down quite simply, but just pointing this out because we will use this much later. The model has three parts. It has a stochastic or a random part, and in this case that means saying that y is normally distributed with certain properties. In fact, almost talk about sigma squared being constant. It has a deterministic part, that's the linear predictor, and these two are joined by a link function. We don't see the link function, there's no need to think about the link function in ordinary linear models because it's the identity link. But if we change the stochastic component so that the expected value of y no longer, here you can see the problem. This deterministic part can take on a value anywhere between plus or minus infinity, and that's a fine property for the expected value of a normal random variable, which can be anywhere between plus and minus infinity. But if we change the distribution from a normal, that can be a problem. So it may not be a problem, but there are reasons why we might want to change that link function from the identity function. But for now, just highlight the idea that we can think of models as having these three components. Once we start to think about maximum likelihood modelling with these three components, we have a great deal of flexibility. We can flexibility in the kinds of responses and the kinds of explanatory variables we deal with, and essentially the possibilities are far wider than if we have to spend our life assuming y might be considered as a normally distributed random variable.